Okay, we're going to talk about the material today from lecture 5, right? On mean, median, mode, a few other little things. As usual, watching these videos is not a substitute for reading the book and notes. Those are your primary sources. Okay, mean, median, mode. I know you've seen this before, probably in high school, but we're going to do it anyway. These are all measures of central tendency. That is to say, they're kind of average or typical values, right? Average or typical values. If you have numerical data, for example, right, it comes quantitative data, it comes from measuring or counting something. Right? You can think of it as points on a number line. Right? There are some points on the number line, and then a measure of central tendency would be a measure of center. That is, it would be some number you could calculate that represented about where the middle of the data was, in one sense or another. If you had categorical or qualitative data, like a list of colors or favorite bands or something, then it might be the value that occurred most frequently, right? The color that more people like than any other color. Okay, before I start talking about this, I need a little bit of notation. We have two different notations for the number of values in a data set, depending on whether the data is population or sample data. If it's population data, we use a capital N. So capital N is the number of data points in a population. Right? Lowercase n, on the other hand, is the sample size, right? The number of points in a sample. Right? Everything we do in this section is done the same way. You calculate the mean the same way, for example, for both population and sample. That is not always true, but it certainly is in this section. But we still need different notations so that we can distinguish them when it's necessary. Okay, so first, the mean. Now, the mean requires you to add and divide things, so it's only for quantitative data, right? And it's only for what's called univariate data, that is, it's a list of single values. So this is for a list of single numbers. Right? If your data is x1, x2, and so on, these would have to be numbers, down to x sub n, right? This would be for a sample, because the little n tells you that. Then the sample mean would be, the symbol is x with a bar over it, imaginatively called x bar. X bar is, well, you add up all the data points, and you divide by the total number of data points, the sample size. Right? This is the average that you've been using most of your life, and by far the most common average or measure of central tendency. The population mean is calculated in the same way. It's got a different symbol. It's called mu. That's the Greek lowercase letter mu. And of course it is x sub 1 plus x sub 2 plus, and all the way up to, and now I would put x sub capital N and divide by capital N. So again, it's just adding up all the values and dividing by the total number of values. Let's do a simple example here. Find the mean of this data. They're computed the same way, so it doesn't matter which one we think of. But let's suppose that this is sample data. Right? So we'll just assume that this is sample data. Now, all this would be then would be, right, x bar. And that would be, well, you'd add all these up. 52 plus 52 plus 54 plus, etc. I'm not going to write them all out. Plus, and then you'd get down to the end and you'd write plus 77 plus 93, and you would divide by 18 because there are 18 data points, and that would turn out to be about 66.94. Right? And as you can see, 66.94 is a pretty good, generally representative value. If you plotted these points on a number line, 66.94 would be in some sense right near the middle. I should say that you should think of x bar, the sample mean, as being an estimator for the population mean mu. That is what it is. If you're talking about the average height of an adult American male, right, our kind of standing example to this point, right, the average for the whole population of adult American males would be that number mu. That's the number we can't get at. So we take a sample and compute the average of the sample, right, and that's the number x bar, and we use x bar to estimate mu. And there's just a little terminology I want to introduce here. We will rarely see it again, but it's worth hearing. Right? Well, there's a quality that x bar has, a very desirable quality for an estimator. And that is, if you take a whole bunch of samples, all of the same size, and find the sample average, the sample mean for each of those samples, right? So you get a bunch of different x bars, and then you average all of those together, it will be pretty close to the population mean. And what's more, if you use larger samples, it'll be even closer. Right? The larger the samples you use, the larger the average of those sample means will get, the closer the average of those sample means will get to the population mean mu. Right? Such an estimator with that property, that when you take a whole lot of samples and average the estimates from them, it gets closer and closer to the population parameter that you're trying to estimate. Such an estimator is called unbiased. It actually does act the way you hope an estimator acts. Right? The larger the samples you use, and the more of them and so on, you get better and better estimates. All right. Let's go on to another one of these, another measure of central tendency. Okay? This one is also only for numerical data. Right? It's called the median. Again, this is probably one you've seen. And the median, all that is the number, or the data point number, halfway up a list, I should say, a sorted list of numbers. So you have your numerical data. You sort it in, by convention, it's always sorted in ascending order, that is from smallest to largest, and you take the number halfway up the list. Well, if there is such a thing. Right? If this is your data set, 1, 2, 3, 4, 5, it's already sorted. Right? My favorite mistake when computing medians by hand is to forget to sort the data first. No doubt you will do the same. Right? But this is already sorted, and if I look, I can see that there is a data point that is halfway up the list, and that would be the median. If my data set were this, though, 1, 2, 3, 4, now I can see that halfway up the list, there just isn't anything there. Right? So what I would do is I would take, for my median, I would take the average of the two points closest to the middle. Right? So that would the mean of those two. So that would be 5/2 or 2.5. And again, right, that seems to be just about right. The number in the middle. When you have to do the median, when you have to find medians by hand, which you'll only have to do a few times in this class, right, you need to know where the middle of a list is. It's pretty easy with a list of 4 or 5 things, but you'd really like to have a more general idea for longer lists. Right? So if you have a list of k items, well, in this case, they'd always be numbers, right? If you have a list of k items, right, then the middle position, not the middle value, but the middle position is the k plus 1 over 2 position. So in this case, for example, right, in this case of 5 items here, well, let's go ahead and do that. K equals 5, then k plus 1 over 2 would be 5 plus 1 over 2 is 3, right? And the third position, 1, 2, 3, third position is the middle. If you have 4 items, k equals 4, then k plus 1 over 2 is the 4 plus 1 over 2, 5 halves, or 2.5 position. That's not necessarily the same as the value in that position. Well, there isn't any value in that position. But the position is the 2.5 position. And of course, this is always going to come out to be an integer, like here, or an integer plus a half, like here. When it turns out to be an integer plus a half, that means there isn't any middle value, and you have to get the median by averaging the two values in closest to the middle. Okay, those rules are written out in detail in the book and notes. But let's do an example or two. Oops. That's not one. All right. So here's the first one. Find the median of the data set, this thing. Now the very first thing to do here is to make a mistake and just pick this by eye, right? And the reason that's a mistake is that you haven't sorted the data in order, right? When you sort the data, it's 2, 3, 4, 7, 8, and it's clear now that the median is going to be 4, right? The middle value. Just for fun, we'll do it with the formula, right? So here, k, the number of numbers in this list is 5, right? And that says that the k plus 1 over 2 position, k plus 1 over 2 is 3, so this says the middle position is the third. So 1, 2, 3, and this says that the median is 4. The median is the value, not the position in the list. By the way, there isn't any really fixed notation for median. People either spell it out, as I did here, or sometimes they just use MED. Your calculator will do that. And sometimes they use Q2 for the median. I often will use Q2 or just spell it out. You'll see why Q2 later on. Okay, how about the median of this data? Now I happen to know this data is already in ascending order, so I can't make that dumb mistake, right? And I happen to know that k equals 18. There are 18 values here. So k plus 1 over 2, that would be 19 over 2, which is 9.5. So this says the median will be equal to the mean of the 9th and 10th values. So 1, 2, 3, 4, 5, 6, 7, 8, 9. There's the 9th. There's the 10th. Both of those values are 67. So this would be 67 plus 67 over 2, which is, of course, just 67. Right? So the median here is 67. Okay. It is a true fact, however unfortunate, that either the median or the mean can be called the average of a bunch of values. But the word average does not have to refer to the mean, I'm sorry to say. It can mean the median also, and sometimes is used to mean the median. Okay, the third measure of central tendency we're going to look at is called the mode. Right? And the mode is just the data value or category, we'll say class, that occurs most frequently. Right? That is, it's the data value or class with the highest frequency. If you had a histogram of the data, it would be the data value or class with the highest bar. It's just a measure that tells you the most common value in a data set. Notice that this can be used, it's the only one of these that can be used for qualitative data. The other two are only for quantitative, but this one can be used for qualitative data as well. Now, often enough, there won't be a single data value or class that occurs most frequently, but there might be two that occur with the same frequency and a frequency that is higher than all the rest. If you had a histogram of such a data set, it would have two bars the same height, and those bars would be higher than all the other bars. You've seen pictures of that already. That kind of data is called bimodal, right? And you report both modes. The reason I'm not writing this out is because it's all in the book and notes, right, which you have to read anyway. Right? So if there's a single value that occurs most frequently, that's the mode. If there are two values that occur with equal frequency and that frequency is higher than any others, then you say that, and when you're asked for the mode, you report both of those numbers. You say, oh, this is bimodal data, and these are the two modes. If there are more than three values that occur most frequently, the data is called multimodal, a word we will almost never use, and you don't report any mode at all. Right? The difference is that multimodal data usually, bimodal data, as we've already pointed out, often means that you have two populations mixed. But multimodal data just means that there's some kind of pattern in the data. For some reason, it keeps reaching a peak and going down and reaching the same peak and going down and reaching the same peak and so on. You need to look at the data, but it's not clear that it has any one most common value or category. All right, let's do a couple of very simple examples. In this first example, we're just supposed to find the mode of each data set. We're looking for a value that occurs most frequently and more frequently than any other. Right? There are two A's, a B, three C's, two D's, and so on. So the mode here is C. Right? The C occurs three times, and that's more times than anything else occurs. What about part B here? A, B, C, two D's, two E's, F, and G. So here you would say the mode is, no, not B, D and E, right? Really, you would say the modes are D and E, and call this data bimodal. How about this one? A, B, two C's, two D's, and E, two F's, two G. This has too many data values that occur most frequently. So you would say here that there is no mode. Right? And here, there is no data point that occurs more frequently than any other. This also has no mode. Okay, here's another one. Here is some data represented in a frequency distribution, right, with classes or categories rather than individual data values. When you have this kind of situation, the mode is still the class with highest frequency. Right? So the mode here is the class 30 to 40 because that's got a higher frequency than any of the others. In this case, just a warning, if this were a multiple choice question, one of the wrong answers would be 13, the actual frequency. The mode is the class or the data value, right, up here. Like I didn't put in this problem here, I didn't say that the mode was 3 because C occurred 3 times. The mode is what is occurring most frequently. And that's the same if you have classes. The mode here is not 13, it's the class 30 to 40. All right. Well, there's a problem that can arise with measures of central tendency when you have what are called outliers. An outlier, right, this is just a data value, and we're talking about numerical data here, a data value that is far from the rest of the data. Right? So in a number line picture, right, you might have something like this. You'd have a bunch of data points on the number line, right? And then you'd have one that was all the way over here, or maybe two. If it were two, you'd probably still say these were outliers. If it were more than two, you would not say that they were outliers. But they have to be pretty far from the rest of the data, right? There's a big gap in here when you put these on a number line. If you were to look at a histogram, and I happen to have one right here. If you were to look at a histogram for this kind of thing, you can see here the data values that occur along here. There are lots of them, right? Whatever these data values represent, let's say it's 1.5 to 2.5, there might be lots of different data points in there, right? There are about, what is that, about 25 or 26 data points lying in here, right? And even more in here and so on. All of this data, if you were to put points on the number line, there'd be lots and lots of points in here. And then over here, there'd be one solitary point far away. Right? So if you have this kind of situation where you have a bar that is one or maybe two data points high, right, that is far away from the others, that you can consider to have an outlier also. Generally, I require there to be about 2 bars worth of space before the outlier, before the single height bar occurs, and then I'll consider it an outlier. If there's only 1 bar of space, that's definitely not enough. 2 bars, you should say, oh yeah, that's an outlier. You may be wrong, but it'll do for this course. Right? What is and what is not an outlier in real work is determined by the data itself. Sometimes you get values that are just really far away from others, and they're perfectly good data. It can happen. Okay, here's an example of what happens. It's kind of an extreme example. It's an example of what happens to the mean and median when an outlier is introduced into a data set. So let me read it. A certain neighborhood contains 50 houses, of which 49 are occupied. The households in the neighborhood have net worths of $1,000, $2,000, and so on up to $49,000. What are the mean and median net worth amounts for the neighborhood, and how will these change when Jeff Bezos moves into the neighborhood in the 50th house? His net worth is $160 billion. Which one, the mean or the median, better represents the neighborhood average? So I'm not going to calculate these in front of you because they're already done here. But here's the average before Bezos moves in, AB, if you will. You would add up all the net worths of the 49 households and divide by the number of households you have, which would be 49, and you'd get a mean of exactly $25,000. You'd also get a median of $25,000, right? If you count it up, there'd be 49 different values here, and right in the middle be $25,000. Okay, after Bezos, you get the mean and median in the same way. You add up all the net worths of the people who live in the neighborhood, right? And then you divide by the number of data points you have, and that the average this time works out to be a little over $3.2 billion. Right? But the median doesn't change very much at all, because all you've done is tacked on one more data value at the end. So all of these remain the same, and you've just got one more. The median just has to move over a little bit. Now it falls between 25 and 26,000 instead of being actually 25,000. So the median is only 25,500. which one of these better represents the average net worth of people or households in the neighborhood? Well, I mean, obviously the median does. Because 49 out of 50, 98% of the households do not have a net worth anywhere near this. It's not a good representation of the neighborhood net worth at all. That's a general rule, which we'll make in just a moment. All right. Let me turn this over and write out these general rules. Sometimes you're going to be asked to find the central tendency, measure of central tendency for a data set without being told which one to use. So then which one should you use, right? So here are the rules. Can we see that? We can see it. First of all, if the data set has a qualitative data, then use the mode. Right? Well, that's a no-brainer. The other two can't be used with qualitative data, right? Mean, median, and mode is all the measures of central tendency we have, and you can't use mean and median with qualitative data, with categorical data. Second rule is, if there is an outlier, or maybe two, use the median. Okay? So if you're asked what's the average value or the best representative value here, and there's an outlier, and it's numerical data, of course, you would report the median. And third, in all other situations, use the mean. So if there's qualitative data, you use the mode. If it's a numerical data set and there's an outlier, or maybe two outliers, you would use the median. And in all other situations, use the mean. We will actually use the TI calculator's one-var stats function to find mean and median. It doesn't find the mode. You have to do that by hand. But we'll use the TI calculator's one-var stats function to find mean and median almost always. You will have to do it by hand a few times. To find out how to use the TI calculator to do it, you should check the book. In the book, there is a video of doing this, and you can see it there, so I won't repeat it here. All right. Next thing I want to do, I want to talk about the weighted mean. This is the last thing in this section. The weighted mean. Okay. The weighted mean is used when you have data from different categories, and some of those categories are more important in some way than others. The most basic example is grades. When you calculate a GPA, you want to weigh grades from, say, 4-credit courses more heavily than grades from 3-credit courses. In fact, calculating GPAs is the only example of calculating a weighted mean that we will see in this class. All right, that's not quite true. We will do expected value for discrete distributions later on, and that is a sort of weighted mean. But as far as explicit problems is concerned, where you have to compute a weighted mean, the only thing you have to do is a GPA. Let me give you the general picture first, and then an example of using it to compute a GPA. All right, so suppose you have k different categories, and you have the weights of the categories are W1, that's the weight of the first category, W2, and so on. Of course, it would be up to WK, since there are k categories altogether. And we're going to say that there is one data value in each category, one number. So the actual data would be x1, x2, and so forth, up to x sub k, where x1 is in category 1, and x2 is in category 2, and so on. Then the weighted mean, and I'm going to use x bar sub w for this. Some people do just write x bar for a weighted mean, but I prefer not to. all you do is you multiply these together, multiply each data point times its weight. So x1, w1, right? And then x2, w2, and so forth. And then you add all those up. You add up all those little products. And then you divide that sum by the sum of the weights. So you would have w1 plus w2, and so forth up to wk in the denominator. All right. As I said, this is not going to be a general formula you have to remember, because the only application we're going to make of it directly is to compute GPAs, but that you will have to do. Here's an example. Last semester, Jasmine got an A in political science, a B in English, a C in biology, an A in movie appreciation, and a D in math. All those classes were 3-credit classes except for biology, which was 4 credits. Assuming the usual scale, A equal 4, B equal 3, etc., what is her GPA? I'm going to do this by laying out a very specific sort of table, and I suggest that you do the same thing. Just do it the same way every time, and you can hardly mess it up. I'm going to need a column for the class. Classes are what? Political science, English, biology, movie appreciation, and what else? Oh, math. I'm going to put in a column for the grade. What did she get? She got an A in political science, a B in English, a C in biology, an A in movie appreciation, and a D in math. I'm going to put in a column for the grade value. The grade value is 4 for an A, 3 for a B, and so forth. So this would be 4, 3, 2, 4, 1. Okay. Now the GPA is going to be here. Oh, no, I'm sorry. I forgot we need a third column, and that is the number of credits. That's actually a fourth column. Okay, I'm not doing so well. But they're all 3s except for this one, right? 3, 3, 4, 3, 3. Right? And these, the number of credits, these are the weights in a GPA. And the data, these are the data values, right? The X's in the formula, and these are the W's in the formula. So in the numerator, I'm going to have each data value multiplied by its weight. In other words, I'm going to have the grade value multiplied by the number of credits. So why not just make a column for that, right? Grade value times number of credits, because I'm going to need that. I'm going to need those to do the numerator. So this is going to be 4 times 3 is 12, and then 9, 8, 12, 3. So the numerator is the sum of this column. This is 12 plus 9 is 21, 29, 41, 44. The sum is 44. And the denominator is going to be the sum of the credits column. So the sum here is, let's see, 4 3s is 12, and 4, that's 16. So the GPA here, is just going to be 44 over 16, which works out to be 2.75. Okay, that's been kind of long, but that's it for this lecture.